multi-class classification. Previously, what we've been doing is looking at binary classifiers. So that just distinguished between two classes, right? But that's typically not what we want to do in a classification problem. I don't want to just distinguish apple, not apple, right? I want to go apple, orange, pear, banana. So now let's explore multi-class classification. There's a couple ways to do this, but really the simplest way, and what we're going to look at as a very good thought experiment, is just to use several binary classifiers, right? All things can be simple, simplified down. And so the most basic way to do this is probably one versus rest. So and that strategy involves just creating a system capable of classifying digits of 10 classes, let's say 0 and 9, by training 10 different classifiers, right? So if we train 10 different binary classifiers, we make a 0 detector, a 1 detector, a 3 detector, a 5 detector, so on. And then we can classify all the digits. And then from each one of those detectors, the instance, the image, will get a score, and just the highest score wins. So we say, let's say 10 number detectors, and highest score wins. So that means that your digit is going to get a score for it being a 1, a score for it being a 2, a score for it being a 3, a score for it being a 4, etc., etc. So 1 versus 1, this approach is the other way that we can do it. And that approach trains a binary classifier for every pair of digits, right? So distinguishing 0s and 1s, and then 0s and 5s, and so forth and so forth. So there are n classes. So, and then we have, let's say, n times n minus 1 divided by 2 classifiers. So if we have 10 digits for the MINS data set, we're going to end up with having to train 45 different classifiers. So the primary advantage of 1 versus 1 is each classifier only needs to be trained on the relevant portion of the training set for the two classes it distinguishes. And so while you have more classifiers, the classifiers themselves are easier to train and easier to model. So they can be more efficient. So let's look at some images here. Now that we know the two types, let's look at some images. So this is a 1 versus rest classifier. And what I have is I've got blue circles, red squares, and orange X's, right? And so I'm going to build a classifier, which is that green line, it's my model. And I'm going to classify blue circles versus everything else. Is it a blue circle? Yes or no? And every instance on that plane, that x1, x2 plane, is going to get a score for a blue circle classifier. Now I'm going to drain a classifier for red squares. And every instance on that x1, x2 plane is going to get a score for is it a red square? And then I'm going to train a classifier for orange x's. And every instance on that x1, x2 plane is going to get a score for is it a orange x. And now each one of my instances have 3 scores. I pick the highest score, and that's what I get, what I classify it as. And it's a perfectly valid way to do a one versus rest classifier. So we can also do a 1 versus all image that looks very similar. Right, and now again, I've got my blue circles, red squares, and orange X's, and I'm only going to train 2 of my classes, right? Everything's got a label, so this is very easy to do. And I am going to train a classifier that says all of my blue circles on this side and all of my orange X's on this side. And then I'm going to train a classifier that's blue circles versus red squares. And then I'm going to train a classifier that's orange X's versus red squares. So if I have 10 digits, then that means I have to scale it to 45 individual classifiers. And that's helpful for certain algorithms like support vector machines, which kind of suffer poorly from scaling. So consequently, like OVO is preferred for such algorithms since it's faster. But for most binary classification algorithms, kind of one versus rest, sometimes called one versus all, is a preferred strategy.